Hello guys, good morning. Good morning to all of you. Is everything all right? Can you start our session? Audio, video, everything is all right? Our session. So today in this session, we'll be discussing group and phase velocity, and along with that, if time permits, we'll go for wave functions. Good morning, Harry. So let us talk about wave packet first. I think you must have heard about this wave packets. In classical physics, a particle is well localized in space. If you, let's say, consider this pen, okay, this is localized at a particular place. But if you consider the wave is not localized at one place. Wave is spatially extended, okay. It is not fixed or localized at some point. So that is what it is talking about. A particle is well localized in space, for its position and velocity can be calculated simultaneously to arbitrary position for classical object. But when we go for quantum mechanics, it is described by a material particle by something called wave function. For quantum particle, wave function is the main thing. Wave function contain all kind of information about the quantum mechanical particle, and you can extract those information by applying different operators. So corresponding to the matter wave associated with the particle, this is de Broglie's conjecture. We have already talked about de Broglie, that every material object has its two aspects, particle and wave. Wave function, however, depend on the whole space, hence they cannot be localized. Theoretically, you see, the wave function is expanded from minus infinity to plus infinity. It is expanded throughout the space. But you see, if we can consider a particle, so it will also have its wave like nature. So what happened? It's like this. In quantum mechanics, we cannot say things definitely. We can only say what is the probability for that particle. So you see, when we consider wave function, it will be like this. Let's say particle is at this place. So you will get some hump or maxima at that position. And at other position, the amplitude will be negligible. If the wave function is made to vanish everywhere except in the neighborhood of the particle, that is what I am talking about. This is a particle. In the neighborhood of the particle, we have non-zero value. At other places, it is negligible. It is then used to describe the dynamics of the particle. So there will be some correlation between the particle and wave. Now that a particle is localized within a certain region of space can be described by matter wave whose amplitude is large in that region and zero outside it. As you can see here, it is large at this region, it is almost zero at some other places. Good morning, Murli. This matter wave must be localized around the region of space within which the particle is confined. So I hope you understand what is this. Every material, in fact, if you consider yourself, you are like a particle, and you will also have your wave aspect. But that is so negligible in classical world that we cannot perceive that. A localized wave function is called wave packet. A wave packet means a group of waves of slightly different wavelengths with phases and amplitude so chosen that they interfere constantly over some small region of space where the particle is likely to be found, and destructively elsewhere where there is a very negligible probability to find the particle. So I hope you got the idea of wave packet. So where the amplitude of the wave packet is more, it means we can consider that the particle is somewhere nearby. So here the probability to find the particle will be more in this region. in this region. So you can see, and as you come out of the neighborhood, you see it is negligible. The particle is represented not by a single de Broglie wavelength. This is very important thing. If you consider one particle, let's say, so it is not like there is only one wave associated with it. It is represented by a wave packet. It is represented by a wave packet. You can imagine. So various individual waves will be there, and it will form a wave packet like this, as it is shown here. Then you take the superposition of these waves and you get the effective wave packet by adding a large number of waves of different frequencies. So this wave packet is mathematically we can represent by the wave function. So we can construct the wave packet, let's say psi of xt, by superposing different waves. So we consider plane waves propagating along the x-axis. How do you represent plane waves? Plane waves means e to the power I times kx minus omega t. So this represents a plane wave, and you can see this is propagating along the positive x direction. This is propagating along positive x direction. Now if it had plus here, then we could say that this wave is propagating along negative x direction. If it is negative, then it is propagating along the positive x direction. If it had positive, then it means that it is propagating along the negative x direction. So these are very fine things. I think you know about this. So we can represent the wave packet by superimposing different waves of different frequencies or wavelength, and we can represent it in this way. You also have seen this kind of expression before. This is precisely very similar to what we have done in the Fourier series, Fourier transform, better way. Psi of xt is equals to 1 upon root over 2 pi minus infinity plus infinity phi k e to the power I kx minus omega t, so dk. So this is like the Fourier transform, right? So phi k is the amplitude of the wave packet. So this is how you represent the wave packet. So what does it mean? This x shows the position of the wave packet, and this time t shown the time at which you are observing. Okay, so let's say at a particular time t, your wave packet may be like this. At some later time, it may go a little bit away. It may be like this, because you see the particle is moving. Particle was here initially. Now the particle has come here. Okay, so based on that particle's movement, you will also get the movement of the wave packet. Now if you consider that at t equals to 0, at t equals to 0, psi of xt will become psi of x0. Now if you denote it, let's denote it by psi 0 of x, psi x0 means now x and t becomes independent, so we can write psi 0 of x. This is the wave function initially, so you can consider it in this way. This is psi x0, this is psi xt. Simple. So what we can write, therefore psi 0 of x, this is equals to 1 upon square root 2 pi minus infinity plus infinity phi k e to the power t equals to 0. So I k x dk. So you can see how can you calculate phi k, which is the amplitude of the wave packet. Phi k we can calculate by taking the Fourier transform of this expression. Phi k is nothing but the Fourier transform of psi 0x. As simple as that. Phi k is the Fourier transform. So 1 upon square root of 2 pi minus infinity to plus infinity psi 0x e to the power minus I kx. Now it will become dx. Here it was dk, now it is dx. So if you take plus ikx for Fourier transform, for inverse Fourier transform it will be minus ikx. Or if you take minus I e to the power minus ikx for Fourier transform, for inverse Fourier transform it will become e to the power plus ikx. So from these two relations, what you can conclude? Let's say this is one relation. So this is one relation. This is another relation. So what you can say, that with the help of this two equation you can go from psi 0x to phi k, or you can also go from phi k to psi 0x. The above relations show that phi k determines psi 0x and vice versa, means from psi 0x you can also go to phi k. Clear? Now you see this wave packet, so as I told you, let's say this is wave packet for the timing. So this wave packet consists of different waves of varying frequencies. So we take the superposition and you get things. So the velocity with which this wave packet moves, that is known as the group velocity. And the crest and trough of the individual waves gives you phase velocity. Remember one thing, that there is no much physical significance of the phase velocity. If I talk about the particle's velocity, that is denoted by the group velocity. Okay, always remember this. For single particles can have more than one wave. Yeah, more than one wave means a single particle cannot be represented by a single wave. A single particle, so it will be represented by a superposition of group of waves, and which makes the wave packet. A single particle will be represented by a wave packet. It can be proved that this fact can be proved, that a single particle does not represent a single wave. Because if you consider a single particle corresponding to a single wave, you will get a relation Vp Vg is equals to c square, and that will make Vp more than c, because your Vg is less than c. So if you want, we can share, I will share the proof in the group. Okay, for the timing, let's focus. Let's talk about phase velocity in a detailed way. phase velocity, which is represented by Vp. So you have understood what is phase velocity. What do you understand by phase velocity? Anyone? Harry, Murli, or anyone? What is phase velocity? Is it the velocity of this individual wave inside the wave packet? That is not completely true. Phase velocity refers to the velocity of the crest and trough. And the phase velocity is the speed at which a point of constant phase, constant phase means like a crest or trough of a single monochromatic wave propagate. Let me give you a physical example. Let's say, no, it is not actually the velocity of the single wave in the wave packet. It is the velocity or speed at which the point of constant phase or crest of a single monochromatic wave propagate. So you see a point of constant phase. So you imagine you have a pond, okay, pond full of water. Now it is plain initially. Now you take a stone, a big stone you take and you just throw it into the water. What will happen? At the projection point, waves will be created and waves will go like this. You see, you will get up, down, crest and trough. So if you consider a circular, crest will be there, then again trough in the circular form will be there. So if you consider a crest in the circular form, you imagine you have dropped a stone into the water, so circular crest will be there. So at each and every point of a single let's say ring, we will have constant phases. So the speed at which those crest moves, that is phase velocity. And you see the overall wave is propagating slower than this crest and trough. So this is a like practical example with which you can understand this, how things work. So if I talk about a single monochromatic wave, then let's take a wave for the wave of the form, let's say psi of xt, this is equals to a e to the power I kx minus omega t. So this is a plane wave propagating along the positive x direction. So what is the phase here? What is the phase here? The phase of the wave is phi. This is the phase kx minus omega t. Now it is the point of constant phase. So phi is equals to constant. So let's set phi is equals to constant. Setting phi is equals to constant. What do you get? We get, so if it is constant and if we take derivative with respect to t, let's say on both sides, so d phi by dt will be 0. This will be k is constant. Okay, k acha k into dx dt minus omega. That gives you dx by dt is equals to omega by k, which is equals to Vp. So Vp is equals to omega upon k. This formula we need to remember. It might travel in one frequency. Yeah, a single wave is traveling with a single frequency, but the wave packet involves the superposition of those frequencies. Okay, it is like that. Let me give you one example so that you understand it in a more better way. You see, let's say, what is the concept of this wave packet? If I take an example, let's say we have this wave, right? This one wave. Another wave is like this. Another wave is like this. Another wave is like this. Now let's consider another wave like this. So you try to understand what I am doing. So you see, at this location, the phases are matching. So what will happen? And others are cancelling each other. So if you add these three waves, what will happen? How it will look like? It will look like this. So the particle is likely to be found here. So this is the overall thing, and in terms of wave packet, if you represent, it will look like this. It will look like this. Getting the point? Now in this relation, the last relation which you have got, we can use energy momentum relation. Energy momentum relation, say E is equals to h cut omega and P is equals to h cut k. What we have? Vp which is equals to omega by k. So this is E by h cut and k is equals to h cut k. So h cut is getting cancelled. So it is E by P. So both of these forms you can use as per your convenience. So I think you have got pretty much idea about the phase velocity. Now let's talk about group velocity. Group velocity. This one I think you have already understood what is group velocity. Group velocity denotes the actual velocity of the particle. Phase velocity doesn't have any significant physical importance or significance. So the group velocity is defined as the speed at which wave packet is like the envelope, at which the envelope of the wave packet, envelope means as a whole, envelope of a wave packet modulated wave after the superimposition. So the speed at which the envelope of the wave packet propagates, that is, it represents the speed at which the energy or momentum is being carried out. The energy or momentum is, let's say, transferred. Well, when a wave is propagating, what does it mean? It means it is carrying energy or momentum, energy and momentum, right? So when wave is moving from one place to other place, means it is transferring energy or momentum from one place to other place. So mathematically, if I want to represent this group velocity, how will you define mathematically? This group velocity is defined as Vg is equals to d omega k by dk. Omega is a function of k, remember, omega is a function of k if you consider dispersive medium, and if you don't consider dispersive medium, then omega is fixed. Okay, so this is general form. Omega is a function of k. Now we can further represent it with the help of the energy momentum relations. So we can use, let's say, E of P. E is equals to h cut omega and P is equals to h cut k. So Vg will become Vg will be, instead of d omega by dk, we can also use it this term d by dp. So this form is also very important. Remember one thing very clearly, that the group velocity represents the actual velocity of the particle. And look at this figure. This envelope as a whole is moving with speed Vg, and the crest and trough is moving with Vph, phase velocity. And you can see, although we have represented by one line, but it is generated by the Fourier transform of individual waves. You can see this is I think we have talked about this in the discussion of Fourier series. In Fourier series, what we have? We have the addition of different waves of different frequencies, right? And ultimately we get this one. So this can also be represented in sinusoidal forms. You know, sinusoidal frequencies, sinusoidal waves of different frequencies can be represented in this way. So this is a Fourier series. Let us now consider some example. Let's say we have a particle which is placed in a constant potential. Now for that case, how we can go with the phase velocity and the group velocity? So let's say for a particle in a constant potential potential V, let's say the energy momentum relation is, we can say E is equals to P square by 2m plus V. Then how do you calculate the group velocity? The group velocity in this case, the group velocity for this case, Vg you know, d omega by dk. So we have just shown it that it is equals to d by dp. So d by dp is what? P by m. Now you see, if you have a particle like this of mass m, it is moving with velocity v, let's say. So what is v? If it is carrying some momentum p, so what is v? V is equals to P by M, because P goes to MB, so V is equals to P by M. This V is the velocity of the particle, right? But here also you see Vg is equals to d omega by dk, d by dp. So taking derivative with respect to P, because V is a constant, so we get v, P by M. So what it says? It says that Vg represents the velocity of the particle. So this, which coincides with the classical particle velocity. We have done this, we do this in classical physics, and we see using the definition of group velocity we are getting a similar result or same result. So we can say that the group velocity is the actual particle velocity. Now what about the phase velocity? The phase velocity can be calculated as V, let's say P. Vp is equals to, you see omega by k was there, so we wrote E by P. So E by P, so derivative, just you have to divide by P. So the first term will be P by 2m plus V by P. Okay. Now if I consider the case of a free particle, for a free particle means the potential is zero. There is no potential acting on that particle. That is why it is called free particle. For a free particle, you know, V is equals to 0. So V is equals to 0, we can say that Vp becomes, by putting V equals to 0, we get P by 2m. So this is P by m is Vg. So this is Vg by 2. So for a free particle, the group velocity is 2 times the phase velocity, or you can say the phase velocity is half of the group velocity. Okay. For a free particle, the phase velocity is half of its group velocity. Now let's go in more detail to understand the difference between group velocity and the phase velocity. Try to understand this is very important. So we can use some mathematical relations to understand the difference between group and phase velocity quantitatively. So VPH or VP, you know, VP is equals to omega by K. So omega is equals to K times VP. So to calculate Vg, we need d omega by dk. So omega is equals to K Vp we have calculated. So d omega by dk, that is Vg, this is equals to K, okay, Vp plus K times dVp by dk. Can you write it? This one is important. So this is Vg. Vg is equals to Vp plus K times dVp by dk. Now what do you know? We know K is equals to 2 pi by lambda, right? So our ultimate goal is to calculate this dVp by dk. So what is dVp by dk? dVp by dk. So if I, let's say, multiply and divide by, let's say, d lambda. So we have taken d lambda extra in the denominator, so we have to multiply d lambda in the numerator. Can I write it? So without violating anything, we have written. Now d lambda by dk. What is this d lambda by dk? Look, k is equals to 2 pi by lambda. So lambda is equals to 2 pi by k. It means d lambda by dk is equals to minus 2 pi by k square. So this is equals to minus 2 pi by k square times this dVp by d lambda. No issue in this. So we require k into dVp by dk, and hence k into dVp by dk is equals to 1 d is cancelled, so it is minus 2 pi by k times dVp by d lambda. Now 2 pi by k is lambda, so it is nothing but minus lambda into dVp by d lambda, and therefore we can write that Vg, which is equals to d omega by dk, which is equals to Vp plus k times dVp by dk, and k times dVp by dk is equals to this minus lambda into dVp by d lambda. So we can just put this value here. So this becomes Vp minus lambda times dVp by d lambda. So this is one form, that Vg is equals to Vp minus lambda into dVp by d lambda. Now we can also write it in this way. We can also write Vg is equals to Vp plus P times dVp by dP. This relation also holds. Vg is equals to dp times dbp by dp, and Vg is equals to bp plus k into dp by dk. Now how this is coming? So we can start from here, k times dvp by dk. What is k? You know p is equals to h cut k, so k is equals to p upon h cut. dvp by dk, so dvp by, let's say, dp, so dp you have taken extra, so dp by dk. Can I write it? Now what is dp by dk? P is equals to h cut k, so dp by dk is equals to h cut, so h cut getting cancelled, so you are left with p times dvp by dp, and that is why Vp plus k dpp by dk is equals to Vp plus p times dvp by dp. So this is a very important result. You may be required to calculate. Sometimes the expression of Vp Vg may be given and you may be asked to calculate the relation between them. So you can utilize this formula. Is it clear or is there any question? Tell me, guys. Crystal clear? Okay. Now there is something called normalization of wave function. Look, before going to normalization, let's talk more about the wave function. What is wave function? Look, as I told you, wave function holds all the necessary information about the quantum mechanical particle, and wave function is nothing but the solution of the Schrodinger equation. Let the wave function of a quantum particle be psi of xt. Now, according to Born's interpretation, this Born's interpretation is quite important. The quantity mod of psi of xt whole square, it represents the probability density. This is also sometimes known as, in this context, if it is called probability density, mod psi of xt whole square, if this is called probability density, this is sometimes called probability amplitude. So this probability amplitude in itself doesn't carry any much physical significance, but this mod square thing represents the probability density of finding the particle at position x at time t. So probability to find a particle at location x at time t is given by mod psi of xt whole square. So you may be given, let's say, some wave function, some expression you will be given, and if you are asked to calculate the probability to find the particle at some position and time, then you can utilize this. And you know, mod psi square is nothing but psi star psi, where psi star is the complex conjugate of psi. Psi star is the complex conjugate of psi. So this is actually if I say it is psi of xt with a star multiplied by psi of xt. So if this is the probability density, if you want to calculate total probability of finding the particle somewhere in space at time t must be exactly 1. As I told you, the wave function, it is expanded from negative infinity to positive infinity, means the whole space is covered, whole space, and whenever the particle is there, there will be peak like this. So if you scan through all the space, it is definite that you will find the particle, right? So that is why, as this mod psi of xt whole square represents the probability density to find the particle at some position, if you scan over the whole space from negative infinity to positive infinity, it is obvious that at one location the particle will exist. That is why the total probability is always one sure event. Somewhere the particle will lie, right, in the whole space. So minus infinity plus infinity mod psi of xt whole square dx is equals to 1. This is known as the normalization condition. Sometimes you may be given a wave function in the form 8 into something, and this is equals to psi. So this, sometimes you may require to find this unknown constant. So we can utilize this normalization condition, which says that it must follow minus infinity plus infinity mod psi whole square dx is equals to 1. So once we apply that, this a can be easily find out. This is known as the normalization constant. This is known as normalization constant. This ensures that psi of xt is square integrable. This represents the square integrable thing. Only such wave functions which follows this property must be followed. Only those wave functions which follows this property, they are said to be physically acceptable, because they yield finite total probability. That is a common thing, okay, that is expected. The total probability must come out to be finite, 1, if the integral diverges psi of xt does not represent a valid quantum state. Any question from this? Look at this. What does the probability density means? You see, this mod psi square is represented. So if you want to calculate, let's say, what is the probability to find the particle between this region, from this to this. So you have to take integration in this range, and whatever value we get, we can say that that is the probability to find the particle between this and this. And as you can see, at this point A, the probability density is maximum, means at the neighborhood of A, the probability to find the particle is maximum. This is a typical wave function. The particle would be relatively likely to be found near A and unlikely to be found near B. So here you see it is 0. The particle is not likely to be found here. The shaded area represents the probability of finding the particle in the range dx. Okay, so it is like what is the probability to find the particle within the region dx. So this is the probability to find the particle in the dx region. Now let's say this is if you go along this side, you will end up in negative infinity. If you go along this side, it means we are moving towards positive infinity. So negative infinity to positive infinity. If you do the total integration, you get the total probability, that is 1. That is your shot. Now let's say if you want to focus at this position, let's say this position is x1 and this position is x2. So in that case, what will you do? You will take x1 to x2 mod psi square dx. So obviously this will be less than 1. Okay, this will give you some finite value. And what does it give you? It gives you the probability to find the particle between x1 and x2. Now if you change the limit, if you, let's say this is x3, this is x4, and if you take the derivative integration between x3 and x4, this will give you the probability to find the particle between x3 and x4. So you now understood, right? If you scan the whole space, if you take the integration from negative infinity to plus positive infinity, you see you will get the total probability. So total probability is always 1. This is probability density. And if you integrate the probability density, we have already read it in mathematical physics, it should be equals to 1, right? So I hope this probability density concept is clear to you. So what you will do if you are given, let's say, a wave function with some unknown constant, what you gonna do? You gonna use this normalization condition to get the normalization constant. How it is less than 1? Because the total is 1. The total probability is 1. If you add everything from negative infinity to positive infinity, that is 1. So obviously when you are scanning a smaller region, it must be less than 1, right? Because the total is 1. So a smaller region means it must be less than 1. And this is clear? Phase velocity does not represent the velocity of the actual particle. It just represents the individual wave, how the crest or trough are moving forward. Okay, na? So the way crest and trough are moving forward, it doesn't matter, na? Because that is not the speed with which energy and momentum is being carried out. What is our main interest? Our main interest is carrying energy or momentum. What is the purpose of wave? The purpose of wave is to carry energy and momentum from one place to other. That is the purpose of wave propagation. Wave is propagating means the wave is carrying energy and momentum from one place to other. But for the phase velocity, it is just the speed at which the crest and trough are moving. So that is why it does not bear much physical significance. Okay. Because that is absurd actually. Mathematically, we are seeing from this relation Vp Vg is equals to c square, right? So Vg, that is the actual particle velocity. So if some particle has mass, it cannot exceed the speed of light, so it must be obviously less than c. Now if the product of two things is c square and one term is less than c, the other term must be more than c. So as it is exceeding the speed of light, so we know the maximum possible speed is c, but here we are getting it more than c, so it must be unphysical. Because if physically valid velocity must be less or equals to c, but here mathematically we are getting it is more than c. That is why it is unphysical. So let us take an example of this to showcase this normalization condition. Let's say I am giving you a wave function psi of xt is equals to a e to the power minus x square by 2. Okay. So find the normalization condition. Now you may ask, what is the purpose of normalization? Why normalization is necessary? Normalization is necessary because this gives you the idea of physically acceptable wave function. By normalizing the wave function, you are making it sure that there, if you scan from negative infinity plus positive infinity, the particle will be somewhere in between. Okay. So by normalizing, we are validating the wave function. Find the normalization condition, find the normalization constant A. So what you gonna do to do this? So you can use the normalization condition, normalization condition. What is the normalization condition? Minus infinity to plus infinity mod psi of xt whole square dx equals to 1. So mod psi of xt means mod of a square, a is constant, minus infinity plus infinity square, so e to the power minus x square dx is equals to 1. That means mod a square, this one you know, square root of pi. So a is equals to a square 1 upon square root of pi. So a is equals to 1 upon pi to the power 1 by 4. You can take the positive results. By 2 is missing. Where by 2 is missing? A square, na? So this by 2 is cancelling. Clear? Let's try this problem. The normalizing constant A for the given wave function is this. Is it clear, Harry, that two thing divided by two thing? Or should I explain it? Minus infinity plus infinity, psi star psi. So psi star of xt, psi of xt dx is equals to 1. Now psi of xt is this, psi star of xt is a star e to the power minus x square by 2. So product of this, a star into a is mod a square, e to the power minus x square by 2 into e to the power minus x square by 2. So that is why e to the power minus x square. Now it is clear. You have to multiply. So 1 e to the power minus x square by 2 here, and from this e to the power minus x square by 2. So minus of x square by 2 plus x square by 2. So that is x square. Now do this one. The normalizing constant A for the given wave function is. You need to understand the given condition, you see psi of x is equals to a times a minus mod x for mod x less equals to a, and here it is mod x greater than a. So you now need to decode mod x less than a means x less than a, as well as you see x greater than a minus a. So it is, we can write it in this way, and this one it means x greater than a and x less than minus a. Means if I consider like this, let's say this is minus a, this is 0, this is plus a. So the value of psi of x is non-zero, x less equals to a and x greater equals to minus a. So on this side it is 0, x greater than a, and x less than minus a. So the value is non-zero in this region only, right, from minus a to a. Clear? Can you do this problem? Simple. Let's use the normalization condition to get the normalizing constant. So use normalization condition. Minus infinity plus infinity mod psi of x whole square dx is equals to 1, right? Now you see we can rewrite this condition. We can rewrite this condition. Let's rewrite psi of x. So if we, as you have seen that it is valid only between minus a to plus a. Psi of x is equals to a into a minus mod x, right? This is for mod x less equals to a. It directly means that, you see, here also we can get two condition. You see, one condition may be x when more than 0, another condition may be when x is less than 0, right? Because a minus mod x is there. So when x greater than 0 means when between 0 to a, when you are considering the positive values of x, 0 to a, then this gives you a into a minus x, and when we are considering minus a to 0, then this gives you a times a plus x, because mod x is equal to minus x minus minus plus. Now we can simply use the normalization condition between minus a to plus a. Instead of minus infinity to plus infinity, we can now use minus a to plus a. Okay. Mod square dx. So a mod a square will be taken common. Now you see minus a to 0. Minus a to 0, what is the value of the wave function? A into a plus x. So it is a plus x whole square. This a square is already taken care of. Plus minus a to 0, now 0 to a. 0 to a, what is the value of psi x? It is a into a minus x. So square hai, so square. And dx will be there. No issue in that. There is dx. There is dx. This is equals to 1. Therefore, mod a square integration. Look, minus a to 0 and 0 to a. So if you replace, let's say, x by minus x, then these two integration will be basically the same, right? So we can write it as 0 to a minus x whole square dx, and this is 0 to a minus x whole square dx. This is equals to 1. So you can just do it in this way. The first one I am talking about, let's say x is equals to minus t. So your dx will be equals to minus dt. Now let's format this table. When it was x, what is the value? Minus a to 0. Minus a to 0. Now for t, the limit will be t is equals to minus of x. So it is a and this is 0. Right. So you see, plus x becomes minus x, and because of this minus, this limit is intended from a to 0, it becomes 0 to a. So this is simple thing. Okay, just simple integration. Now both of these terms are same, so you can write 2 times mod a square 0 to a minus x whole square dx is equals to 1. Now we can just simply expand this expression, a square minus 2x plus x square dx is equals to 1. It means 2 mod of a square, and what is this value? This is a square x minus a x square by 2, so 2 to get cancelled, and x cube by 3. The limit is taken between 0 to a, and this will give you a cube minus a cube, so a cube by 3. So this becomes 2 a cube by 3 times mod a square is equals to 1, and that means a is equals to 3 by 2 a cube to the power half, and that is matching with option B, right? Look, little bit lengthy calculation, but simple at the end. Let me know if you have any confusion in this calculation. Is it clear? Now one problem I am giving you as homework, you will try to do it at home. Simple problem. At t equals to 0, particle is in the potential V of x equals to half m omega square x square, and its wave function is this. So this is not necessary potential, it is just to format the question. Wave function is given by this. So here what is the normalization condition? Constant, it is A, right? N is the energy eigenvalue with energy, this, where n equals to 0, 1 to 3. Value of A so that A is normalized. So although other things are there, but the main question is to apply the normalization condition and to find out this normalization constant. Will you be able to do it? Look, when you write mod psi square, this is called ket n. For psi star, you will get bra n. Bra n means this is bra n. So when you calculate mod psi square, this n and this n, it will become 1. Okay. So this one, this n ket will be removed. Okay. For the time being, I am just telling you this. We will later discuss about this when we will be dealing with mathematical tools. Then it will be very much easier for you. This is actually bracket notation, bracket notation. So this bracket notation we will talk about later also. For the time being, you just use a simple logic and try to find out the normalization condition. Okay. Just imagine that this thing is not there. You can do it. Chalo. So let's end the session here. Thank you guys. Thank you very much. Bye bye. Take care.